My name is Dr. Scott Nowicki. This is Geology 100 Natural Disasters. The topic today is climate change. I'm going to attempt to describe the entire story of climate change, but in order to do that, I'm going to have to break it up into three different pieces. To begin with, we're going to talk about the mechanisms by which the Earth's climate changes, and the mechanisms that stabilize climate over long periods of time. The second piece of the story is the geologic, the glacial, and the biological record of climate and atmosphere that we have available to us, so we can see how the climate and environments have changed over this long period of time. And then finally, we'll be able to get to these potential future scenarios and the likely outcomes. Now, of course, there are many other things we're going to need to discuss after that and along the way, and we'll pick up those pieces as we get there. Let's begin with the atmosphere. The atmosphere on Earth is very unique. It is the only atmosphere of all the planets that we know of in the solar system and in the galaxy that has had life affecting it over geologic time. 78% of the atmosphere is nitrogen, 21% is oxygen, 1% is argon. Those are major components of the atmosphere. Everything else that we know of is a very small percentage. Water vapor can vary between actually a couple of percent and 0.1%. Carbon dioxide is somewhere around 397 parts per million. That means if you have 1 million particles of atmosphere, you could count out 397 of them. Methane is somewhere around 1.8 parts per million. Nitrous oxide is down to 0.3 parts per million, and ozone is in the parts per billion. Some of these gases have been around since the formation of the planet, such as nitrogen and argon, while some of them have changed drastically over geologic time. Oxygen is one, water, ozone, and some are currently changing. Carbon dioxide, nitrous oxide, methane. These are drastically different from these kind of long-term stable atmospheric gases. So we are really concerned with solar radiation on the Earth because the sun and solar radiation is the source of all our energy, and more importantly, that sun is what heats up the planet. And what's really important are the different wavelengths of light that come from the sun. Somewhere out to this millionth of a meter in terms of wavelength, that's approximately where this visible and near-infrared radiation occurs. So this is all the light that we see from the sun. But of course the sun is producing a lot more high energy to the right and shorter wavelength radiation, and it's also producing a whole lot more longer wavelength and lower energy radiation to the left. If the energy is somewhere around this visible into the ultraviolet, we refer to that as short wavelength radiation. If it's somewhere into the infrared and further, we refer to it as long wavelength radiation. So solar radiance, meaning the total amount of photons or energy coming from the sun, when it hits the surface of the Earth, it's highly controlled by the atmospheric composition. Turns out the sun radiates energy in a Planck function. That means that this outer curve shows how much energy, watts per square meter per micron, is being generated from the sun. So there's a peak, and that peak tends to be around the visible portion of the spectrum. This gray plot shows the solar radiation as though you would measure it at the top of the atmosphere. It peaks in the visible and then drastically drops off in both higher wavelength and lower wavelength. But when that sunlight comes through the atmosphere, certain atmospheric molecules get in the way and they absorb some of that radiation. Rather than matching the upper curve as the sun moves through as the solar energy comes through the atmosphere, it gets absorbed by water, and therefore it's decreased slightly in this little absorption feature. And thanks to oxygen and some more water, it gets absorbed pretty significantly in this wavelength. And then again and again and again, water, carbon dioxide, oxygen, ozone, these are all absorbing energy preferentially in certain wavelengths. Ozone and oxygen, water, carbon dioxide, these are important molecules that are absorbing solar energy as they come through the atmosphere. The greenhouse effect, as we see it on Earth, is a phenomenon that retains heat on the planet because solar radiation is peaking in the visible portion of the spectrum. We saw that from that Planck curve, that the maximum point of energy being produced by the sun is somewhere around the visible. And then most atmospheric gases are transparent in the visible wavelengths. However, the surface interacts with visible light, it heats up and emits thermal radiation So those same atmospheric gases that were transparent in the visible portion of the spectrum then absorb this thermal energy as it passes back out through the atmosphere. Here's the sunlight coming in, and a lot of the sunlight is able to make it through the atmosphere and hit the surface. Some amount is reflected off of clouds, some amount is reflected off the atmosphere itself, but a good portion of it makes it all the way through the atmosphere to the surface. Once that solar energy hits the surface, it hits you and me and cars and trees and dirt and houses. It heats those things up, and it converts this short wavelength radiation, this visible wavelength radiation, into longer wavelength radiation, turns it into thermal infrared energy. And at that point, this thermal infrared energy gets radiated back out into the atmosphere. Some of that energy bounces back down, it actually reflects off the atmosphere. Some of that energy makes it through, but a good portion of that energy actually gets absorbed by those same gases that were transparent to these visible wavelengths. As sunlight hits the surface, as it makes its way through the atmosphere once, heats up the surface, and then tries to work its way back out to space, it gets trapped in that greenhouse atmosphere. Now, the temperature of the surface affects the processes that distribute heat and water all over the planet. Because sunlight is reaching the surface, it is heating up and causing evaporation of water on the surface. And so there is this exchange of energy going from sunlight to actual thermal temperature energy. That same heat increases the temperature of the atmosphere, it causes clouds to form, and then as these clouds move around the planet, driven by the winds from heating and cooling surfaces, there's this distribution of water all over the place. So there's this ongoing cycle of energy coming in some cases evaporating water, in some cases causing plant life to grow, and this large-scale cycle movement of heat and water all over the planet. Now, over time, this global climatic system tends to equilibrate. The atmosphere and the ocean deliver heat from the equator to these higher latitudes. If there's more energy hitting at the equator, that means that the ocean currents will drive this circulation a little bit faster. The second is that if there is extra greenhouse gas, the planet heats up a little and transfers more energy into the ocean and atmosphere. If there's not enough greenhouse gas, the planet then cools down and reduces the amount of heat transfer. If there are more greenhouse gases or less greenhouse gases, the system will equilibrate to take advantage of that condition. Now, the causes of climate variation are all over the place, but they tend to be either cyclic or forcing in one direction or another. We're going to talk about orbital dynamics, and these are classic cycles in terms of climate variation. The second type of climate variation is due to forcing. Now, forcing, instead of being a cycle where it increases and decreases at some relatively regular time, forcings tend to push it in one direction or another. It either heats up the planet or cools down the planet as a function of physical changes. An important forcing is biological. As plants and animals evolved on the planet, they effectively pushed the climate as they moved in these different ecological niches. As continents crash into each other, they uplift mountain ranges and they change the way that energy moves around the planet. They change the way that ocean currents can actually distribute energy. The third is meteor impacts. If there's a large-scale impact that occurs, it can drive the climate in one direction, and it actually drives the climate in two different directions over time. And then the last one is volcanism. There's a bunch of volcanic eruptions that occur that can dump a huge amount of ash into the atmosphere, and very similar to meteor impacts, really drive the way the climate is interacting. So we're going to start with eccentricity, and another word for eccentricity is ellipticity. The best way to look at ellipticity is to think about it in terms of how circular an orbit is. So in this picture, the sun is in the middle and the Earth is buzzing along on this circular orbit. As the Earth orbits the sun, the distance between the Earth and sun doesn't change. Therefore, the amount of energy that the Earth receives doesn't change. As opposed to an eccentric orbit, this one on the right, it is not a circular orbit, it's a bit more elongated. The more elongated it is, the more likely that the Earth, as it's buzzing along on this orbital path, will receive less energy when it's over here and more energy when it gets close. So this change in ellipticity or eccentricity is actually going on all the time. Now, the important thing is that the Earth's orbit doesn't stay like this, and no planetary orbit just stays in a constant ellipticity. It turns out that it's changing over time. Meanwhile, there's another process occurring that is called precession. This is the same reason why as you spin a top, it's spinning at a high RPM, but it starts to circle around at a relatively slow rate. That slow circling is what's known as precession. It is this additional dynamic that occurs along with spinning. And then finally there's obliquity, that as the Earth, obliquity is the angle at which the Earth spins relative to the plane of the solar system. And it turns out as that obliquity changes, the amount of energy that hits the poles versus the equator changes. What this means is that over long periods of time, tens of thousands, hundreds of thousands of years, we can actually map out the changes to our orbit and therefore the changing amount of sunlight that we receive as a function of precession, obliquity, eccentricity. We have a plot up here that shows precession. As the top is spinning and it's slowly working its way around, there's this small scale back and forth and then this larger scale kind of increasing and decreasing in the total amount of sunlight that's being received as a function of precession. The next one down, obliquity, is a slightly longer time scale. 41,000 years are these obliquity cycles. And then this eccentricity is again a longer time scale where it goes up and down 95,000, 125,000, and 400,000 year scales. So we've got a small scale precession at 20,000 years per cycle. We've got obliquity at 40,000 years per cycle, and then eccentricity at 100 to 400,000 year cycles. In the end, what this really produces is this solar forcing, an increase or decrease in the total amount of sunlight and therefore total amount of energy that the Earth is absorbing from the sun. Looking at it over the past million years, there are times when there is more energy and times when there is less energy when you combine all three of these effects. So these variations in the Earth's orbit have been correlated with glacial cycles, and that's what you see on this lowest plot down here. These are the stages of glaciation. When the total amount of energy changes drastically and there's more energy on the surface, the Earth tends to heat up. And when there is less energy hitting the surface, the Earth tends to cool down. So if this is now on the left, we are currently in one of these warm stages. And we have been for the past 10,000 years or so. Now as you go further into the past, you can see that temperatures dropped. So if you were around 20-some thousand years ago, it was significantly cooler. Here's 125,000 years ago, and again, it was as warm as it is today, and then it dropped again. So each of these gray areas are warm periods, each of these white areas are glacial periods. So this shows that simply over hundreds of thousands of years to millions of years, we can see these orbital dynamics changing the climate, and it has been noted and seen in glacial sediments, in varves, in these lake sediments, identified by Milankovitch and therefore named the Milankovitch cycles. So we can both see them in the rock record and the sediment record, and we can model them in terms of orbital dynamics. There is a cycle to the sun. It's approximately 11 years long, so that you get these maximums and then minimums that are occurring on a regular basis. Now it turns out that the total variation is incredibly small. It's less than 0.1% of the total amount of energy coming from the sun. So we often don't really notice these. Maybe we'll have some more solar storms during these high years and less solar storms during these low years. But as you can see, we've been working our way through these solar maximum and minima all throughout human history, and it really hasn't caused too much trouble.